Have you ever heard of Earth's magnetic pole reversal? It's a phenomenon that has happened multiple times in the past. Scientists have discovered that the magnetic field of the Earth flips, causing the north and south magnetic poles to interchange positions. This reversal happens over thousands of years, during which time the magnetic field weakens and the poles wander. The last time Earth experienced a magnetic pole reversal was around 7,000 and 80,000 years ago. Some scientists believe that the next reversal is overdue and could happen in the near future. What causes this mysterious phenomenon? The Earth's outer core, comprised of molten iron and nickel, generates the magnetic field surrounding our planet. The movement of these metals creates electric currents, which in turn produce the magnetic field. As these metals move and flow differently in the outer core, the magnetic field can become unstable and eventually reverse. A magnetic pole reversal, also known as geomagnetic reversal or polarity reversal, is a gradual process where the Earth's magnetic field weakens, becomes more complex, and eventually reverses direction. While the exact mechanisms behind pole reversals are not fully understood, scientists believe they are linked to changes in the Earth's outer core, where the planet's magnetic field is generated by the movement of molten iron and nickel. During a pole reversal, the magnetic field may weaken to about 10% of its current strength, leading to a significant decrease in its protective effects against solar and cosmic radiation. This weakening of the magnetic field could potentially expose the Earth to higher levels of radiation, which could have implications for both technology and living organisms. Navigation systems that rely on Earth's magnetic field, such as compasses, may become less reliable or require recalibration during a pole reversal. Additionally, animals that use the Earth's magnetic field for navigation, such as birds and sea turtles, may experience disruptions in their migration patterns. Changes in Earth's outer core play a significant role in the dynamics of the planet's magnetic field and can contribute to geomagnetic reversals, including pole reversals. The outer core is a layer of molten iron and nickel that surrounds the solid inner core. It extends from approximately 1,800 miles to 3,200 miles beneath the Earth's surface. Heat from the Earth's inner core drives convection currents within the outer core. These currents cause the molten iron and nickel to move in a circular pattern, like the motion of boiling water in a pot. The interaction between these convective currents and the rotation of the Earth creates a dynamo effect, generating the planet's magnetic field. Variations in the composition and density of materials within the outer core can affect the behavior of convection currents and the generation of the magnetic field. Changes in the distribution of elements such as iron and nickel, as well as the presence of lighter elements like sulfur and oxygen, can influence the flow patterns and heat transfer within the outer core. Changes in temperature and chemical composition within the outer core can result from a variety of processes, including the cooling of the Earth's interior over geological timescales, the crystallization of the inner core, and the mixing of materials from the Earth's mantle. These changes can alter the viscosity and buoyancy of the molten materials, affecting the dynamics of convection currents and the generation of the magnetic field. Geodynamic processes such as mantle convection and plate tectonics can also influence the behavior of the outer core. Movements of the Earth's crust and mantle can introduce mechanical stresses and changes in pressure that propagate into the outer core, potentially affecting its temperature, composition, and flow patterns. The circulation of molten iron and nickel in the Earth's outer core is what creates the magnetic field. Any changes in the flow patterns, temperature, or composition of these materials can affect the generation of the magnetic field. Geomagnetic instabilities refer to fluctuations and disruptions in Earth's magnetic field that can occur over various timescales, ranging from seconds to thousands of years. These instabilities can manifest as irregularities, fluctuations, or even reversals in the Earth's magnetic field strength and orientation. Understanding geomagnetic instabilities is crucial for comprehending the dynamics of Earth's magnetic field and its interactions with the planet's interior, atmosphere, and external influences such as solar activity. One form of geomagnetic instability is secular variation, which involves gradual changes in the Earth's magnetic field over decades or centuries. These changes can include shifts in the location and intensity of the magnetic poles, as well as alterations in the overall structure and strength of the magnetic field. Complex processes, including convective motions and interactions between the core's many layers, are what cause secular fluctuation in Earth's outer core. Abrupt variations in the secular variation rate or geomagnetic jerks, are defined by sharp increases or decreases in the magnetic field's velocity. These events, which typically last for a few years, can have significant implications for navigation systems, satellite operations, and geomagnetic modeling. The causes of geomagnetic jerks are not fully understood but may involve interactions between the Earth's core and mantle, or changes in the distribution of magnetic materials within the outer core. Geomagnetic excursions are short-lived deviations from the prevailing polarity of the Earth's magnetic field, during which the magnetic poles wander and may even temporarily reverse before returning to their original orientation. These events are recorded in geological deposits and paleomagnetic data, providing valuable insights into the behavior of the Earth's magnetic field over geological timescales. Geomagnetic reversals are rare events that occur over thousands of years, and their causes are still the subject of scientific investigation. While reversals have occurred numerous times throughout Earth's history, they do not follow a regular pattern, and their triggers remain uncertain. The Earth's magnetic field is not static but undergoes constant fluctuations and variations. Sometimes these fluctuations can lead to instabilities in the magnetic field, which may eventually result in a pole reversal. External causes that may contribute to pole reversals, also known as geomagnetic reversals, involve factors outside of Earth's core and can influence the planet's magnetic field dynamics. While the precise mechanisms linking external factors to geomagnetic reversals are still not fully understood, several potential contributors have been identified. Variations in solar activity, particularly solar flares, coronal mass ejections, CMEs, and the solar wind, can exert considerable influence on Earth's magnetic field. Intense solar activity can induce geomagnetic storms and disturbances in Earth's magnetosphere, potentially leading to geomagnetic instabilities and perturbations that could contribute to geomagnetic reversals. High-energy particles from cosmic sources, such as supernovae explosions and galactic cosmic rays, can interact with Earth's atmosphere and magnetic field. These interactions can produce secondary particles and ionize atmospheric gases, creating disturbances in the Earth's magnetic field and potentially contributing to geomagnetic reversals. Interactions with the Milky Way galaxy and other celestial bodies within the galaxy may also play a role in geomagnetic reversals. Gravitational forces exerted by nearby stars, as well as the overall motion and dynamics of the Milky Way, could influence the distribution and behavior of cosmic rays and other high-energy particles that interact with Earth's magnetic field. Changes in Earth's orbit and axial tilt over long time scales, known as Milankovitch cycles, can affect the distribution of solar radiation and the planet's climate. These orbital variations can indirectly influence geomagnetic processes by altering atmospheric circulation patterns, ocean currents, and the distribution of mass and heat within the Earth's interior, potentially contributing to geomagnetic reversals. Interactions with external magnetic fields from other celestial bodies, such as the Sun or nearby planets, could influence Earth's magnetic field dynamics. Variations in the strength and orientation of these external magnetic fields could induce changes in the Earth's magnetosphere and contribute to geomagnetic instabilities that may lead to reversals. Complex interactions leading to pole reversals involve a combination of internal processes within Earth's core, external influences, and feedback mechanisms that collectively shape the behavior of the planet's magnetic field. The planet's magnetic field is produced by convection currents in the outer core, which are fueled by heat from the inner core and gravity. This process is known as the geodynamo effect. Variations in the flow patterns, temperature distribution, and composition of materials within the core can influence the stability and orientation of the magnetic field, potentially leading to geomagnetic instabilities and reversals. Solar phenomena such as solar flares, coronal mass ejections, and the solar wind can induce geomagnetic disturbances and perturbations that may trigger or exacerbate geomagnetic instabilities. Cosmic rays from galactic sources can also interact with Earth's atmosphere and magnetic field, influencing the behavior of the magnetosphere and potentially affecting geomagnetic processes. Geomagnetic feedback mechanisms involve interactions between the Earth's magnetic field and various processes within the planet's interior and surrounding environment. These feedback mechanisms can amplify or dampen geomagnetic instabilities, modulate the rates of geomagnetic reversals, and influence the recovery and stabilization of the magnetic field following a reversal. Processes such as mantle convection, plate tectonics, and changes in the distribution of magnetic materials can contribute to geomagnetic feedback mechanisms and shape the behavior of the Earth's magnetic field over time. Studies of ancient rocks, sediments, and geological formations provide valuable insights into the occurrence and behavior of geomagnetic reversals throughout Earth's history. Paleomagnetic data reveal the timing, duration, and intensity of past reversals, as well as associated environmental and climatic changes. By studying these interactions and processes, scientists aim to unravel the mysteries of geomagnetic reversals and their implications for the planet's past, present, and future magnetic environment. Past pole reversals, as evidenced by geological records, have occurred over thousands of years without causing mass extinctions or major disruptions to human civilization. However, there is no evidence to suggest that a magnetic pole reversal would lead to catastrophic events such as mass extinctions or major disruptions to human civilization. Thanks for watching the video. Don't forget to subscribe to our channel for more interesting content.